Well, thank you very much. I'm not sure if you can hear me and can see my slides.
Yes, yes, it's all good. We can hear you. We can see the slides. It's all good.
Perfect. Okay. Well, I would have loved to come to Munich, but unfortunately, in this week, I'm a director of a summer school and I'm sitting in a hotel in Crete, in Greece. Well, I would have liked to come because ASM is one of the topics that impressed me very much by the work of Yuri. And in fact, I think ASM would have deserved much more attention. At least the standard version of ISM, the sequential version, has a beauty of simplicity and a generality of what an algorithm is that is really much more adequate than this, say, symbol crunching automata that we are used to denote as an algorithm. When it comes to the parallel or the distributed versions, well, let me say, I was not so convinced that what I have seen so far was the last thing you should speak about, but that is my topic more or less today. So let me start with my first or my second slide. Let's start very simple. What is an algorithm? So I give you just some examples, and we should not discuss is this or that an algorithm or not. It's just more the question, well, you will see. So the first Euclid's algorithm, of course, it is an algorithm. The bisection algorithm that gives you an input as a input is a continuous function, a real number, two real numbers, three real numbers, and output is again a real number with f with f of c smaller than epsilon. Of course, it is, and this is already an interesting point. It's very simple to write this down as an abstract state machine, but you cannot implement it as it is because you cannot implement continuous functions and real numbers. So this is already a question whether or not it is an algorithm. The alternating bit protocol that detects and corrects a loss of errors in messages. Also, you can ask, what does this compute? The hiring procedure of new staff in a company, it is an algorithm, it's up to you. The organization of a bakery, a robot assembling a circuit board, a cooking recipe, the apple sort algorithm. I don't know if you know that you have an inclined board which holds in it increasing size, and apples roll down, and eventually each apple will fall through a hole. So you can sort the apples in this way. Do you denote this as an algorithm? I leave it to you. Stock exchange. In stock exchange, a lot of things happen, and again, you can ask, is this an algorithm? So what is the effect of these algorithms?
Sorry, Wolfgang.
Yeah,
We have Janos Makowski. He's asking if he can have a question.
Janusz can always have a question. Yes, of course.
In the bisection algorithm, what is the use of A and B?
F of A is smaller than 0 and f of B is bigger than 0. This is a well-known algorithm.
Yeah, well, it doesn't say it. I don't understand.
Sorry, I didn't say it. Yes.
Okay, thank you.
You are welcome. Okay, so let's look at what the effect of these algorithms are. Euclid's algorithm is a real number. Bisection algorithm is also real. Sorry, Euclid algorithm is a natural number. Bisection algorithm is a real number. Alternating bit detects and repairs loss of messages. Hiring procedure is the result somebody got a work contract. Organization, a bakery, at the end means a client gets the bread. Functions, a robot assembling a circuit board has the effect that there is a functioning circuit. A cooking recipe has the effect that a meal is served, etc. Sorted bin of apples, and with a stock exchange you become rich or poor. These are the results of those algorithms. And again, this is not the standard way of speaking about algorithm. And then come, in recent times, the problem of really big systems. For instance, computer integrated systems in any kind, business information systems, information infrastructures, internet of everything, of whatever you want, cyber physical systems, digital infrastructures, digital ecosystems, systems for health and mobility, in Industry 4.5, or even nowadays 4.0, even 5.0. What do they have in common? Well, what they have in common is that there are digital systems and they have discrete states and steps. And what we require to do is, what we need is an integrated theory to cover all these kind of digital systems. And of course, the classical theoretical computer science cannot do this. So the question is, how can we do it better? And then I think Yuri had a wonderful idea to say, let's consider a much more general kind of structure, namely what Tarski told us in the 1950s. You can comprehend any mathematical structure by help of what they call first-order structures or algebras or Tarski structures. You can denote as you want. These kind of structures do already help a lot to understand much better those general systems. And I have, in brackets, I have written mathematical structures, but in general, you don't need, it's not important that these are mathematical structures. And I will come to this in a minute. First, let's again consider what is such a kind of a structure. What is it? Well, a heterogeneous structure of this kind. It has finitely many domains, finitely many constants, finitely many functions over those domains. And in some versions, and in the version I consider it is important, you have also finitely many relations or predicates over those domains. And to make it very clear, a domain may be finite, it may be countable, infinite, it may be uncountable, like the real numbers. It may even be, the functions even may be computable or non-computable or continuous. Whatever functions you have, it is completely irrelevant for the concept of this kind of structure, and that is important. And also, non-numerical worlds are important. And as an example, I make a very simple example what's happening in the bakery. And here you see some domains. You have pastries. You have 3 pastries. You have descriptions of pastries. You have a constant pastry. You have 2 propositions, which are special predicates. And here you have a number of predicates. I come later on back to this. You have functions. And this is already a wonderful structure to define a bakery, to define the constant aspects of a bakery. Okay. Now let's come back to abstract state machines, and what the idea of Yuri was, comprehend a state as a structure. So the structures are used to describe states. And dynamics of systems, there is the idea update the states. So how can you update the state? To describe the dynamics of an update of a state, you update a function at an argument by a concrete value. So dynamics is described by updating functions. And the rest, when you make one local update, the rest of the structure remains. Now, how do you describe this kind of updates? There you need a signature. So for each structure, you have a signature. So what is a signature? You have a symbol for each domain. You have a sorted symbol for each function, a sorted symbol for each constant, and in my version also sorted symbols for predicates. So the game between symbols and what they denote is very clearly specified in this kind of structures. Okay. And now when you make an update, you update a structure S by, and the result is the structure S prime, then you use the same signature for both S and S prime. And the update rule, now I tell you a little bit about the abstract state machine. There's a rule, and here you have a symbol F, the FET, as presentation means. This is a symbol of the signature, and there you have 2 arguments. These are arguments of the structure. Namely, the element A is replaced by the element B. And then you write this in the usual way by f of a becomes b. Okay. And then you can make it conditional and say, if I'm surprised that you don't see my arrow, but it's okay. Conditional update means if you have a proper, if a predicate P is true, then you update in this way. So this is the update rule of ISMs, and an ISM program is just a set of conditional updates, and the step from S to S prime is the application of a program to a state. And how it goes in detail, I think you have seen a little bit by Nachum already, and this is standard. Okay, so far I have not told you anything new, but just what ASMs do. And now I make a slight variant of this. It seems to be slight, but at the end it turns out to be very significant. So what we do, we skip this. We don't update functions, but we update the predicates. So I only update predicates, and to describe dynamics, I update the predicates, as I said. Now I can look to your heads, and I know what you think. You think but the rest remains. Every function is a predicate, every predicate is a function. So what is the big fuss of this? There is not a conceptual fundamental difference, but there is one, and I show it to you. The updates are completely different. The updates of functions that we have seen means you take one argument and to replace the value at this argument by another value. The predicate updates, you can update predicates much simpler, because you just say the predicate P no longer applies to the element D, or the predicate P from now on applies to the element E. So what you do is you change the predicate with respect to one element. And I like Nachum's I liked that Nachum was the speaker before me, because he addressed a problem that is so well known. Since the 1970s, people address this problem. So, and the background of this problem is, what are the fundamental atoms of dynamic behavior? What is the fundamental atoms of behaving in an algorithm? And so far, everybody assumes that we have variables that are written or read, and writing and reading variables or stores. This is the fundamental stuff. And here we see it is not. The fundamental operation is not reading and writing variables, but the fundamental elements is putting something in a box, so to speak. The predicate is a box. Put something in or take something out. And this put in, take out is much more simple than reading and writing predicates. Okay, that is the message here. And in this context, that each function can be simulated by a predicate and vice versa is no longer relevant. So let's look a little bit into this fundamental idea. D leaves P. What does this mean? T is an element, P is a predicate. So if you have the predicate in the state S and you remove the element D, then you get the new predicate in the state S prime. And if E attains Q is a predicate, then you say you take the predicate as it is in state S, you put in the E, and then you have the predicate Q in the state S prime. That is the fundamental idea, and I make just now a drawing for this. So the predicate is drawn as a circle, and inside the predicate we put all the elements to which the predicate applies. For instance, inside is D. Okay, and when we put something out, we make an arrow and a box, and so you can interpret the box as it moves something out. It moves the D out. And the result is P S prime, where the D is no longer in. Okay, let's do the same with Q. In Q, there's at least the element E is not in. And when you put something in, then the E is in. And the effect of putting this in with this arrow and the box is graphically written this way. Now what we can do, we can say this, both of these things, sorry. Yeah, both of these things can happen at the same time. Now, something it does not. I haven't, but it's just make it jumps. It doesn't work properly. So what we have made here is the box, the two boxes that you have seen here. Here, these are two boxes. You just glue the boxes, and then the result is this. Okay. And what you made is you made a step where in the predicate P applies the predicate in state S, predicate P applies to D, and now it does no longer applies to D. And in the predicate Q in state S does not include E, and now it includes E. So this is in one step, two things happen, and even more in one step can happen that you update, you move two things out of predicates and you put in two things into other predicates, and you can also make sequences out. You can compose it this way, and here you see already what concurrency now means. After this event has occurred, then there are two events occurring independent of each other. So you get independence simply by the idea that the effect on predicates is local. If something happens, then it applies to a limited number of predicates, and if two things happen with detached predicates, then they are concurrent. That is all, and that is very simple in this formalism. Okay, so of course now you can ask about the expressive power of all this. Is this new idea of updating predicates as powerful as the idea is of updating functions? And I just give you an example to show you that it is. The example is we traverse the natural numbers. So we have a signature, domain elements, constant symbols, unary function, and a concrete structure here is the domain is the natural numbers, the constant is 0, and the unary function is the successor, and the predicate is the actual natural number, the actual number that is present. And you have the structure as n, where you have this is as 0, and for each n you have a constant n and Yuri function successor, etc. Predicate numbers like this. And as an ASM rule, we can now have the constant function is the constant symbol, or the constant c is updated by applying the function f to c. So if c is 0, then you get 1. If 0 is 1, then you get 2. And in this formalism I have shown you, you just update the actual predicate. So actually, initially it's 0, and then this event occurs, and then the 0 is replaced by 1, and then by 2, and then by 3. And if you iterate to apply the abstract state machine rule, then you also apply the update predicate. Okay, that intuitively shows you these are more or less equivalent. In a sense, I must admit, I have not written it down formally, but intuitively it's clear that you can express everything you can express by an abstract state machine. You can also express this way. Okay, at this point, I would have stopped originally, but fortunately, I think we all got a paper that Bertrand Meyer will present on Sunday, and there he spoke about the question of that you have pure mathematics. He is intending to speak about the idea that a programming language is pure mathematics. And let me talk about this a little bit. So I think I have some minutes free. So what we want to have is kind of a syntax-free concept. And thanks to Bertrand Meyer, I want to say something about this formalism, because also this formalism is in this way a little bit of pure mathematics. So what I have learned in my first courses on programming languages, I learned a programming language, what does it do? It attaches the meat of semantics onto the skeleton of syntax. I think we all have this learned in the 1970s, and it's a more elegant formulation is what Floyd told us 1976. he assigned meanings to programs. So program is syntax, meaning is semantics, and he assigned in a systematical way meanings to programs. And Bertrand Meyer quotes this, and he also quotes Abrial's paper, who turns this around and says assigning programs to meanings. He says what we want to have. Nobody wants to have a syntax. Everybody wants to have the semantic, the thing that happened, that can happen. That is the intention of the program. And what Bertrand then says, he says, meanings are programs. It is only a kind of a representation problem. And programming really is simple mathematics. That's all to Bertrand Meyer. And all is based, what he bases on is sets and elementary operations on sets. And he says more or less, syntax is just to make large mathematical expressions better readable. That's his message, and I'm looking forward to his talk on Sunday, where he will talk about this in more detail. I think this is a wonderful idea, and it works, as he will show you, very well for programs. But my question is, does it also apply for modeling? Because what I have shown to you is not a programming language, but a modeling language. And I think what we have seen, modeling is also really just simple mathematics when you do it in the way I've shown to you. But it's not based, as Bertrand says, on simple sets. It is based on structures. And that's why I've spoken so much in detail about concrete structures. So when you have these structures, which are anyway the basis of predicate logic, take them and make a modeling theory based on this. And that is good for this, the good basis for all the kind of digital systems that I have shown to you. And dynamics just means update predicates and not update variables. Okay? So the static aspects of a system are just given by the terms of the signature, because interestingly, the predicates do not contribute to the. I have not spoken to this, but of course, terms are built from the symbols of a signature. The terms are not contributing to the signature, but they contribute to the description of behavior. Okay? And immediately you inherit everything that you get from first order logic. And now I come back to a fresh look to modeling. PetriNets so far have been explained as consisting of places and transitions, but nobody could say what a place or a transition is. Now we can say, well, and this is still syntax. Now we can say we don't start with places and transitions, but we start with predicates and changes of predicates. And the static aspects are described by domains and functions, and dynamic aspects are, as I said, change of predicates. And this is pure mathematics, I think, in the sense that Bertrand has intended to say. I hope you see this difference. And at the end, I would like to come back to this bakery example. So I don't go into the details of this structure, but I show you a little bit how you can understand this bakery. So initially you say the next thing to be baked is pie. So pie here in quotes is just a description of pies. Here you construct a concrete pie and you put it on a counter, and then it goes to an 8, and the 8 moves. It moves on the shelf, and then you sell it, and then you start with the next. You could start with the next with the next pastry to be baked. But this is not what we make here. What this box says, in the minute that the pie is moving around here, in this minute you can already start to bake the next bread. So this is a highly concurrent system already. And here we say, what is the next thing to be baked? That is a bread. So here we have a circle where you produce something, and here you have a circle where you consume something, and you have a buffer in between. And the two cycles are synchronized, that is true, but they are completely concurrent in the rest of the time, and this concurrency is given you for free, more or less. And why is it so simple? Because you don't update variables, you don't read and write variables, but you put into predicates and you take out of predicates. Therefore, it is so simple. Okay, that's all what I wanted to say.